So we're going to continue with the argument we saw in the previous lecture. I mean, we said many things about random matrices of different kinds, right? There were Wigner matrix and covariance-type matrices. And then we started working on the problem of bounding the operator norm of a random matrix of Wigner type. And actually, we're being even more specific. We're saying that we want to consider a matrix whose entries are Gaussian, right? Normal random variables, IID, with mean 0 and variance 1, on the diagonal and above the diagonal. So below the diagonal, you do what you have to do to have a symmetric matrix, right? Which is this thing here. And then we started describing a method. The method started from this Epsilon Net idea. So if you have an Epsilon Net for the sphere in n dimensions, so it's an n-1 dimensional manifold. And we showed that you always have an Epsilon Net of this size. Right, just to remind you, okay, what is an Epsilon Net? It means that you have the sphere. For any vector here, you have another vector which belongs to the Epsilon Net, such that the distance between the two is less than or equal to epsilon. And then we showed that, well, in principle, bounding this soup is hard because we have infinitely many vectors, right? An uncountable number of vectors here. But we switched from this problem to a discrete problem, where in order to bound this, you only need to know how it behaves over an Epsilon Net, which is a finite object. Right? And then we said, okay, so what does this imply? It implies the following. That the probability that the operator norm is, say, greater than R. Okay, let's take epsilon equal to a quarter here. Right? So in this case, the coefficient here becomes 2. Right, the value of epsilon that you choose doesn't matter too much as long as it's less than 1/2, so that you have something well defined here. Right, so let's say we can all agree on this. So the probability that the operator norm is larger than some R, it's at most the probability that the supremum over the Epsilon Net is, well, times 2, right? This factor you get from here. Right, so if you want this to be larger than R, then you need this to be larger than R. So, and of course I can move the 2 here, have R over 2. But then this is the same as saying the probability of the union of the vectors in the Epsilon Net greater than R over 2. Right? Haven't changed anything. I'm just saying, well, if you want the supremum, it's a finite set. So you just need one of these to be larger. The probability of a union is less than the sum of the probabilities. And now we want to bound each one of these terms individually. We know how many terms we have in the sum. So it's some exponential in n. And we want to bound each one of these terms individually. And I said at the end of, around the end of last lecture, that in this case where the entries of the matrix are normals, then it's very easy to find a bound for this. So in the notes, I have a more complicated bound for a slightly more general family of matrices that you can have. But I'm just going to do the simple case here. So, okay, let's say that you fix a vector in the unit sphere. Well, maybe a vector in the Epsilon Net, which is contained in the unit sphere. Right. So what is this random variable like? Well, I need to do a little bit of linear algebra, but it's a sum over I and j equal from 1 to n of vi, vj, x, ij. Right? Well, some terms here are repeated, right? So let me say what they are. So you have a sum for the diagonal elements. And then we know that xij, for I and j different, xij equals xji. So I just want to count these terms once. So clearly this is a sum, or let's say a linear combination of random variables that are of the form n01, or of independent random variables of this form. And we know that when you have a linear combination of Gaussians like this, then the distribution, so of the sum is just another Gaussian with mean 0, right? But it's easy to see that the mean is 0 here. You just take the mean term-wise. And in order to get the variance, you must sum the squares of the coefficients. So you get a sum here. Okay, well, with some sort of S term here, and now I want to find what this S is. So has everybody seen this? When the next lectures are going to be? So we have lectures tomorrow and on Friday, besides today. So let's see what S is. So first you have to sum the squares of the coefficients over here. And then you have a sum for I less than j of the squares of the coefficients here. Right? And well, here I'm summing over I less than j. This is the same as summing over all I that are different from j. So I can have one, well, except that I have to divide by 1/2, and this is a 4, right? So it's the square of 2 here. And this is almost what we want. Well, there's a factor of 4 here. So now what I can do is, well, if I fix I, this term is fixed here. And then I get a sum of Vj squared, right? So we know that the sum of Vj squares, if you sum all of them, is just 1, right? You have a vector on the unit sphere, so this is the square of the norm. So here you're summing over I different from j. So what you're going to get is well, so 4 moves over here. You have twice the sum I equals 1 to n, vi squared, 1 minus vi squared. Sorry. And then you can see what's going to happen. So you get twice the sum of the square of the vi's, which is again 1. You get the sum of the 4th powers, but you subtract twice that sum of the 4th powers. Right? So this sum is at most the sum of twice the sum of the vi's, which is 2. Right? So you have a very nice and clean bound, no matter what v is. So why is this important? Well, there are many things we know about Gaussians. Let me quickly argue that if you have that the probability that the absolute value of a Gaussian being larger than x is less than e to the minus x squared divided by 2 sigma squared. Right? It's just a bound, right? But I mean, essentially any bound of this sort would be fine. This is a bound that's very easy to prove. Why is that? So, right, so let's write this probability exactly. So how do we compute probabilities for Gaussians? Well, we just integrate the density, right? So we have the integral from x to plus infinity of e to the minus t squared over 2 dt divided by 2 pi. This is the probability that a normal, well, sorry, there's a sigma squared here. This is the probability that the normal is larger than x. You also need to compute the probability that the normal is less than minus x, right? Is this clear? And of course, these two probabilities are the same because the normal is symmetric, right? So you get twice this thing here. And okay, x is greater than 0 here, right? Or greater than or equal to 0. So now I'm just going to do a change of variables. I'm going to replace t by u plus x, right? And then I have an integral. Well, this 2 is going to cancel the square root of 2, so you get something like this. Right? Haven't done anything yet. Up to now, everything's exact. Except for now, I'm going to use the fact that this squared here, it is larger. I mean, what's the squared quantity here is larger than u squared plus x squared. Right? Because it's u squared plus x squared plus a term that's 2 times u times x. Both u and x are non-negative, so this you get this lower bound here. Okay, so what does this give you? It gives you exactly this, so it gives you this is less than right? Because you have a lower bound for this, but you have e raised to minus this, so you get an upper bound for the integral. And now it's very easy to see what happens, right? This is a constant, so it jumps out. And then you have this thing here. And what is this? Well, you go back to this expression here. This is just the probability that your normal, mean 0 and variance sigma squared, is larger than 0, which is 1. Right? And then you have so you have the bound that I said, right? That the probability that a normal with variance sigma squared is larger than x is e to the minus x squared twice sigma squared. So why does this matter to us? Because now we can apply this bound over here, right? So this is the x we want. Well, the variance we want is this quantity s here. And s, we showed, it's hard to compute s exactly because you have something like the sum, 1 minus the sum of the fourth powers. But we have an upper bound, which was, sorry, it's 2 minus the sum of the fourth powers. We have an upper bound of 2, and it's easy to see that instead of using a variance here, you use an upper bound, you still get an upper bound for the probability. So what I mean is that you can pretend that, you can just say that sigma is equals 2 here, more or less. Right? That will give you an upper bound. And now the upper bound is going to be like this. So the upper bound is, well, you have n terms in the sum, and you have an exponential. So you're going to get sigma squared down here times 2, which is 4. You get r squared divided by 2 squared, which is also 4. So you get right. So let me write this down. Right. So this is kind of the first part of the method. This is the second part. And so this is where I computed the variance, or an upper bound for the variance. So we conclude that the probability that the norm of Wigner matrix, the operator norm, is larger than R for all R. So remember, we used the half net, right? So, sorry, a quarter net. So I mean, we took epsilon equals a quarter here. So that gives you, well, 1 plus 2 times 4. So it's 9 here. And now the question is, how large do we need R to be for this bound to be good, right? So clearly, R equals 0 is not good enough, right? You get that the probability of this being larger than 0 is less than 9 to the n, which, of course, is much worse than the usual bound that the probability is at most 1. But so you have to play with this a little bit, right? So if you take R to be equal to a constant, this is still very bad, right, if n is large. Right? Here we're thinking that n is very, very large, and you want to find an R that makes this small. So, okay, it's not very hard to figure out. So let's say you just want this to be less than delta, right? So you need to make 9, well, okay, let me write the logarithms here. So I need a log, okay, log of 9 times n minus r squared 16 less than or equal than log of delta. And now you just move things around. You get r squared over 16 should be more than log 9 times n plus log of 1 over delta. Right? Because when you have a minus in the front, that's the same as taking 1 over delta here. And then, well, if you only care about how this grows with n for a given delta, right, it's clear that you need r to be something like the square root of n. Right? Because you just need to take the square root here, then you get the square root of n plus this. But we're thinking that somehow this is smaller than this or something. So, so let me state a precise theorem anyhow, which so the theorem is as follows. So there exists a C greater than 0 such that the probability that the norm of a Wigner matrix, an n times n Wigner matrix, is larger than C times the square root of n, and that this is going to be less than e to the minus n. And remember I said that we care about n very large, right? So you're just saying that, well, the probability that this bound, that this norm is much larger than square root of n times a constant goes to 0 very fast with n. And what's this constant? Well, you have to figure it out from here. You want the probability of, you want delta to be e to the minus n, so this is going to be n. So the constant is something like, well, there's 16 times log of 9 plus 1, and then you take the square root of, well, you take the square root of that. Okay, so maybe I should, if I'm not mistaken, I think this should be 4 times log of 9 plus 1. But the main point is that this constant here doesn't depend on n. I mean, remember I told you last class that you can actually get very precise bounds on the largest eigenvalue and the smallest eigenvalue. So in principle, you know a lot more about this quantity here than what I just wrote. But the method that we use here is actually very general. And it's a method that works in many different kinds of problems, as we're going to see now. So this idea that you first, well, you want to look at a supremum, right, which gives you the operator norm. So what you do is you first discretize, and then you take what we call a union bound. You prove that this, right, after you discretize, you have finitely many events. So the probability of their union is just the sum of the probabilities. And all you need is a very good bound for each one of these probabilities to make everything work. And the very good bound in our case comes from the fact that we have Gaussian random variables, but in the notes you have what people sometimes call sub-Gaussian random variables, for which essentially everything works in the same way. So for instance, you could look at matrices with the same ideas. You could look at matrices where the entries are plus and minus 1 with equal probability. And everything would go through. And actually, if the matrices are, the entries of the matrix are bounded and have mean 0, everything goes through as well. Only the value of the constant will change. Right, so any questions? I think this means no. Okay. Right, so this is one of the two kinds of random matrices that we wanted to consider. And for the rest of the segment, I'm going to talk about the other kind of matrices, which are these covariance-type matrices. I'm going to remind you what they are. So, right, well, let me write anyway the setup over here and then finish erasing the board. Oops. Right, so if you remember, well, the setup we had IID random vectors who lived in p dimensions, right? So the matrix that we're interested in, the random matrix, is this one over here, is the kind of the covariance, the empirical covariance matrix associated with these vectors. And there's, we hope that this matrix is somehow close to this one. And yesterday we said, well, we looked at this least squares problem where we showed that if you knew something about this matrix, then you could have a very nice bound on the how well least squares does. Right? And well, what is it that we needed to know? We needed some statement of the sort. We needed to prove something that said, like, for all v belonging to Rp, that that v sigma v is less than alpha times v sigma hat v. Right, for some alpha greater than 1. But so this is one goal that we could try to prove, that to prove that this holds a very large probability, right? The result we just proved said, well, the operator norm of a Wigner matrix satisfies this property with very large probability. So we'd like to prove something similar here, right? For some alpha greater than 1. But we're actually going to prove something stronger, which we don't need for the least squares problem, but it's something that you might want for different problems. So we want to prove that if you look at this difference here, that this is less than epsilon times V transpose sigma V. And why is this stronger? Well, it's not very hard to show that if you have the second inequality here, you have the first one with alpha equals 1 plus epsilon. Right? Because you have that, well, the difference between this and this thing here is at most epsilon times this. So, oh, sorry, you get it with, yeah, so it implies the first one with alpha equals 1 over 1 minus epsilon, if you want. But in any case, it's a stronger kind of property. Here you will want to control one, you want to prove that this quadratic form is lower bounded by the expectation. And here we want a two-sided control. We want both upper and lower bounds. And why are we doing this? Well, because essentially, this is actually a kind of a point at which recent research has shed some light. Until not too long ago, proving lower bounds like this one, it was essentially as difficult as proving the upper bounds. Or the method that I'm going to show you, which is the same method essentially that we used for the other problem. What it did was you couldn't just get a lower bound from it. All you could get were two-sided bounds. But there are recent papers by several different people actually. Many people had the same idea around the same time that you could prove lower bounds by different methods. And I mean, the paper by myself and the references is one of those papers, and there's references to the other papers that did that. So, right. So we're going to prove this sort of property, but then there's some things that you might notice. Right. So let's first look at what happens. So what you want is something like this. So. And let's remember that we assume that this matrix here is invertible. Right? Well, okay, have an absolute value. Well, if the matrix is invertible, it means that we can replace V with, say, sigma minus a half V, or W. And what happens to this expression here is this. So notice that, well, okay, so what happens to this side? You get W, well, the sigma minus a half W, sigma 1 half W times epsilon. And this whole thing here is just, well, you get W, you get sigma minus a half times sigma minus a half. So the matrix becomes the identity here. And you just get the epsilon times the norm of W squared. Right? Is this clear? Yes? No? Maybe? Okay. What about here? Right? So here it's a bit more complicated. Well, again, you have V inner product sigma V. It's going to become just a norm of W. So, okay, this is what we want, right? And this is a transformation you're doing to the problem. And so you're going to get one term here. It's going to be just the norm of W squared. And what about the other term? It's going to be something like V transpose sigma minus a half sigma hat N sigma minus a half V, W, sorry. Well, this is a sort of a weird matrix, but there is a meaning to it, which is this. which is this is the covariance type matrix for different vectors, which I'm going to call x tilde I, which are these vectors over here. Right? You just need to check the calculations and see this is exactly what you get. And what is the expected covariance matrix of this? Well, it's going to be sigma minus a half, sigma, sigma minus a half, which is just the identity. So so what we want, well, remember, this is what we wanted originally. This is a different problem, but it's a kind of an invertible transformation of the original problem, so it's equivalent. These two things here are equivalent. And now, so what we really want is okay, let me give a temporary name to this matrix here. What we want is that this is true, right? Because this norm here is just inner product of W and W, and this for all W. Right? So what is this really? I mean, you have this expression here. If and only if you have the same thing when you restrict to vectors of norm 1, right? Is that clear? Suppose that this holds for all W of norm 1. It's also true for all other vectors, right? Because any vector is a vector of norm 1 multiplied by a constant. And when you multiply by a constant, you get the square of the constant on both sides. So what you really want is that for all W in the sphere, but of course, if you take a vector of norm 1, then you don't need to have the norm of W here. And what is this thing? This is a symmetric matrix, right? So we know that if you take a symmetric matrix, matrix A, say, and you look at the maximum of inner product of W times AW over all W of norm 1. That's exactly the operator norm, right? And we've been saying this several times. So what we want is that this matrix here has an operator norm less than epsilon. So why am I doing all of this? I mean, I'm just saying, I had this sort of lower bound problem for sigma hat, and I'm doing a harder problem, which is a problem of getting both upper and lower bounds. And what I'm saying is that I can express this problem as the problem of proving that a certain random matrix has a small operator norm, which is the same kind of problem that we had before. What is this matrix Cn? Well, is it a covariance type matrix? Yes, you just change the vectors, right? So it's the same kind of problem, and so what I want to prove, so the problem I want to address now and is you have your vectors x tilde I. Well, let me actually call them xi. IID, and let's assume that their covariance matrix is just the identity. And you want to prove that the operator norm is small with high probability. So what have I done here? I'm just saying, well, I mean, it's a bit like when you prove the many theorems in basic probability, right? Just saying, well, I want to prove a theorem that applies to any sequence of independent random variables. And one of the first things that we do is to say, well, we can assume that all those random variables have mean 0, well, if they're IID, say. We can assume they have mean 0 and variance 1 just by subtracting the mean and then dividing by the standard deviation. Okay? So what am I saying here is that, well, you can assume that this random covariance matrix here, or these random vectors, that their covariance matrix is the identity. Right? So this is like changing the variance just by multiplying by a constant, right? Well, here the constant is a matrix. And so you only need to consider the case where the covariance matrix is the identity. And the old goal that we had for the original problem is equivalent to proving that this operator norm is small. Right? So from now on, this is the problem that I'm going to work with. So let me change this over here. I'm just going to assume that this thing here is the identity. And the goal you want to prove that the probability that this is less than epsilon is very close to 1. But we're going to do this in a very special case. Because this actually, I mean, I show you the problem for Wigner matrices. For Wigner matrices, we understand everything very well. We understand that, for instance, if you have IID entries, then essentially what you need to get the same result as in the Gaussian case is that you need IID random variables with a mean 0, variance 1, and bounded fourth moment, or finite fourth moment. If the entries are not IID, then you need a little bit more. It's a bit more complicated, but understand everything very well. This problem here, well, by now we understand it fairly well. There are still open questions, but we have a much better understanding than we used to about this problem. But still, it's very hard. So I'm going to do things in the nicest possible case, just like I did for the Wigner case. So I'm going to assume that these vectors here, they are normal with mean 0 and covariance matrix equal to the identity. And it's like I'm cheating, but it turns out this is useful for the things we're going to do later, so this is good enough. And as I said, I mean, the getting bounds for even slightly less nice vectors is much, much more complicated. So the current best results tell you that you need some sort of a condition on the moments of these vectors of order 8 plus epsilon for some epsilon. And then you get a very complicated proof. With a lot of effort, you get a bound. But it's much, much more complicated than what I intend to the kind of thing that I intend to show here. And still, there are open questions. I mean, it's very clear that the current methods are not optimal. So we're going to just do things in this case, and you're going to see that they're not that simple, even in this case. Right, well, the first few steps are simple. So and let me just make sure I've got the constants right here. Right, so the basic method's still the same, right? So I have this, I'm going to use an Epsilon Net kind of argument. But then we're going to see that, well, in the previous case, once you took the Epsilon Net, then we wanted a bound for V in a product matrix times V. And that was very simple because it turns out that this random variable, this inner product, was a Gaussian random variable with a variance we could compute. In this case, it's not Gaussian anymore. Though I mean, it's not so bad, but it's, I'm going to see what it is right now. Right, so, yes? No, I'm just assuming. That's an assumption. So that's. Yeah, if you have, instead of Gaussian random vectors, you have sub-Gaussian random vectors, meaning that the one-dimensional marginals have similar bounds as for the Gaussians, then everything works. But yeah, but then if you want to do even things that are slightly worse than that, saying the bounds on the one-dimensional marginals are exponential instead of Gaussian, which is like exponential of the square, right? If you want to do even that, is very complicated. So, and then getting down to 8 plus epsilon moments, so finite number of moments, is even worse. So this is essentially the only case in which you can give a proof that only lasts 30 minutes if you omit some calculation. The other proofs will last, I don't know, 3 hours. It will be very complicated. Right, so the first part is just to take an epsilon net and just to argue that, well, the probability that Cn minus the identity operator norm. Okay, I have two epsilons here, so I want to take a quarter net as before. So this probability here is less than the probability that there exists a vector in the quarter net such that V transpose C hat n, oh, sorry, this became sigma hat n. Right? And then again, we're going to do the same thing. We're just going to say, well, this is less than the sum over all V's. Right, this is a union of events, right? The probability that exists a vector satisfying this is the probability of a union of events of this form. So the probability of the union is at most the sum of the probabilities. So now we need to understand these terms individually. And this is where it becomes more complicated in this case. And yes, so first of all, we need to know what this looks like, right? Well, let's expand this thing here. So you get V hat sigma n V minus norm of V squared, which is just 1, right? Because the epsilon net is contained in the sphere, or the quarter net. So this is a sum. We know what this looks like, right? This we saw last class that this is just the sum of the squares of the inner products of the xi's with V. So it's something nice, right? Because let's see why. Well, the fact that xi is normal zero identity means that xi V is normal with mean 0. Now we have a scalar here, right? You have a one-dimensional thing. And what is the variance? It's just the norm of V squared, right? Which is 1. So we know in particular that the mean of this guy is just the mean of the square of a normal random variable, and know that's 1. So for any fixed V, we know that this sum here is a sum of IID random variables, and you're subtracting the mean. So there's and when you, by the law of large numbers, you expect this to go to 0. But of course, that doesn't really help us much because we need a rate. We need to know this goes to 0 at this speed so that we can bound this sum. Right? And so how do we prove such a rate? Well, as I said, it's much more complicated in this case than in the previous case. So I'm going to state the rate right now, and then I'm going to sketch how you justify it. Right? So, but I mean, whatever this is, right? So now, from now on, I've fixed V in the epsilon net. So what I have, so this is just a sum in distribution that is equal to a sum of ni squared minus 1. Well, these are normal 0, 1 variables squared. Right? And now I have this bound here. Where's the bound? Yeah. So I have this. Oh. And therefore, any t between 0 and 2, is it 2? Yeah. The probability, okay, this is, I need to subtract I. The probability that this sum the probability that the absolute value, right, which is one we want to bound anyway. Probability that this is larger than t, this is less than twice e to the minus t squared n over 16. It's a bound. I'm gonna give you some idea of how to prove it. But let's leave this bound and see where it takes us, right? So let's see how we prove how we can bound this expression here. Right. Right, so let's apply the lemma. So we already knew that this is bounded by the sum, right? And notice that the bound I have here, I mean, in this case, I can guarantee that all the terms in the sum are equal, exactly equal, right? Because everything I wrote here is exact. I'm just saying that the distribution of this is the same as the distribution of this, which doesn't depend on V. So in this case, I mean, but all you need is an upper bound. But in this case, because things are now Gaussian, the distribution of this random variable doesn't depend on the choice of V. And you can just say, well, so this is at most the size of the epsilon net, or the quarter net, times the probability of a single event. And the event, as we showed, is an event of this form. And let's see what we have here, right? So there are a few things that you need to take care of here. So what's the size of the epsilon net? Well, the 1/4 net. What we said before is that if you're in dimension n, then you have an epsilon net with size 1 plus 2 over epsilon raised to n. But here, the dimension is not n anymore, right? These matrices here, they're not n by n. They're p by p. the size of the matrix is dictated by the dimension of the M-int space, which in this case is P. Right? So, and here you have a quarter net, so you have 1 plus 2 divided by a quarter raised to P. So there's going to be 9 to the P before we had 9 to the N. And this thing here, well, all we need is we need some condition on epsilon, right? So let's say from the outset that epsilon is less than 1. And then you get here twice e to the minus epsilon squared n divided by 16. Now let's say again that you want to make this probability less than delta, like what we did before. Right? So the calculation you have to find is, well, given, so here let's say I fixed epsilon, I fixed p, and I fixed delta, and I want to know how large n needs to be in order to get the good bound. In other words, if you're really talking about studying covariance matrices, you're saying, well, how large do I need my sample size n to be in order for my empirical covariance matrix to be close to the true covariance matrix with high probability? So you have 9 to the p, well, twice this e to the minus epsilon squared n over 16 less than delta. So then you have log 2 plus p log 9 minus epsilon squared n 16 less than log of delta. And then you can play around a little bit more. What you're going to get is this. So you need n to be larger than 16 over epsilon squared. Log 9 times p plus log of 2 plus log of 1 over delta. In other words, if you take the theorem is this. So if n is this, then the probability that the random covariance matrix is more than epsilon far from the identity, this is less than delta. Right, so, and I mean, you can see a very general scheme, this general method in the proof, right? You get all those ugly numbers, and you only state the theorem at the end because you don't know what they're going to come out like. So you just pretend you know what you're proving all the way until you get to the end, and then you see, I need n to be this big, and then you say it. I mean, there's something to this comment, which is that in general, this sort of method where you apply these epsilon nets and then you bound the probability of the sum by the sum of the probabilities, these methods tend to be very loose. So they never give you, or they almost never give you the optimal constant. So here you're just essentially you're saying, well, n grows like p over epsilon squared times log of 1 over delta times epsilon squared. So this you can actually prove that is optimal. That if you take n that's much less than p over epsilon squared or something like that, then this is not going to work. But the constant here, all those numbers, 16 times log of 9, you shouldn't trust them too much. They're not real. Well, they're real numbers, but you see what I mean, right? Yeah, so and let me just give you an idea of how you prove the lemma. And, well, first of all, is this clear? I mean, is it clear how this theorem here follows from all these ugly calculations? Right? Take the net, right? You discretize, then you take the net, then you notice that for any vector v, you have a sum of IID random variables of specific kind. squares of normals. And then you use a bound for the sum, for the concentration properties of the sum, and you're finished. Right, so let me just give an idea of how to prove the lemma. Yeah? Right, so, I mean, the idea is that somehow I said that this proof is not very sharp, but the idea somehow is that it's not very far from the truth, in the sense that, well, when you do this bound, you're saying, well, I want to control this family of random variables here, and the complexity of this family of random variables is essentially P, in the sense that it's sort of a P-dimensional family of random variables. If you want to approximate, well, the complexity of approximating these random variables grows exponentially with P. Okay, so maybe this is not a very good intuition, but what I'm going to say right now is sort of true, which is that in many of those settings, you have this very large family of random variables, and it's not too terrible to say that if you take different vectors V, so V's that are sort of nearly orthogonal to one another, that these random variables are more or less independent from one another as well. Nothing that I said is particularly true, but you can look at the covariance of these random variables. It depends on so if you take this random variable and you take a different V, the covariance is going to be very small unless V and the other vector are very close to one another. And because we know, well, so if you look at the sphere in P dimensions, you can get exponentially many vectors that are sort of nearly orthogonal to one another. So you can get exponentially many variables that have small covariance. Okay. And I mean, if you have, in this case, you can actually do much more. So in general, if you're looking at vectors, I mean, not necessarily normal vectors, but you can look at this asymptotic setting where P is growing within, and xi is a vector with independent coordinates that have mean 0, variance 1, and bounded fourth moments. Then you have something called the Bio-Ink Theorem that tells you that essentially this epsilon squared here is optimal. So I mean, there's very specific cases in which you do like, you take n to be equal to P, you assume that epsilon squared P, where is it? Epsilon squared n over P converges to some constant C. And then you can prove that this is essentially optimal. You can get you actually get a law of large numbers for the largest and the smallest eigenvalues of this matrix. And you can see that this sort of very vague and fishy reasoning that I present to you is good in some sense. Right, so what about the lemma, right? So that's the thing that's missing here, how you prove such a lemma. I mean, I just want to give an idea for people who took the mini course on concentration inequalities. This is going to look familiar. And this is because this is a concentration inequality, right? You're looking at a sum of ID random variables. You want to know how close it is to its mean, typically. And, there's essentially one way to prove concentration inequalities, except, Michel Talagrande has a different way, but outside of that, there's only one way. Well, maybe there are 3 ways to prove them, but there's kind of 99% of all papers are written with this way that I'm going to present. Right, so the lemma's over here. So maybe I just erase everything that's to the left here. And in the notes, I have a very complete proof of this concentration inequality, so I don't need to, if you want, you don't need to copy this, or it's going to be sloppy anyhow. Right, there's a very general way, if you have, say, a random variable here, and you take its mean. Right, so instead of proving this inequality, what's the probability of the absolute value being larger than t, I'm going to prove an inequality where I take off the absolute value. and take off this 2 here. And the proof on the other side is sort of similar. So there's a very general method for proving an inequality on this quantity here, which is, well, it's called Bernstein's trick. So you fix a positive number, and you notice that this event here is exactly the same as this. Right? I mean, x minus expectation is larger than t if and only if the exponent here is non-negative. So this is exact. But here you have a random variable that's larger than or equal to 0, so it's non-negative. And you look at a probability that it's larger than 1. Then you have an upper bound, which is just Markov's inequality, which apparently was proven by Chebyshev. And Chebyshev, Markov proved Chebyshev's inequality, so that's one anecdote we got from the concentration course. So you can just take e to theta x minus t, right? And then you see that this is actually, well, because exponentials are nice, you actually have the product of 3 exponentials here. Right? The exponents just add up. And these 2 are constant, so you can move them outside. And this is true for any theta greater than 0. So if you get a bound of this form, in the end, you can always optimize over theta to get the optimal bound. So if you want, you can say that this is equal to the infimum over positive theta, infimum over positive theta, infimum over the positive theta. Why do you need to make this bound useful? Well, you need a good bound on this. Right? So what's our setting like? In a setting, x would be the sum of the squares of the normals. And e of x is just the mean of the sum, which is 1, right? Each random variable here has a mean 1. Right. So now you have a situation that tends to be very favorable, which is you want to bound the moment generating function. This is what this thing here is called, of a sum of independent random variables, right? So of course, the sum becomes a product. And because the random variables are independent, right? You're taking the product of independent things here. And we know the expectation of a product of independent things is just a product of the expectations. You need to be slightly careful in that. Well, for that to work well, you need either these things to be non-negative or to be integrable in some sense. But everything's fine here because they're all non-negative anyway, right? So independence and it's even nicer, right? Because in this case, we know that all of these random variables have the same distribution. So there's a square here, of course. So this is actually the same thing for I equals 1, 2, 3, or n. So you're going to get, because they're IID, you get just the first term raised to the nth power. Now you need a bound for this. But now, I mean, in this case, in this particular case of Gaussians, you can do explicit calculation and figure this out. And let me just very quickly point out what the calculation would be. And yeah, so it's, okay, so how do you compute something like you take xi, it's going to be theta over n. How do you compute this? You have a standard normal random variable. How do you compute this expectation? Well, we know how to compute expectations, right? You just integrate against the density. And it turns out to be a especially nice integral. Because you can do a very easy change of variables here. Well, first of all, you notice that what you have here is z raised to minus t squared over 2, except that you get a prefactor. Right? So you're going to need theta to be less than a half for this to work. Otherwise, it's very clear that this becomes unbounded. Right? And so you get this. So now you do a change of variables, which is just to take u to be 1 minus 2 psi t. And this becomes 1 over, so you get this factor here out of the change of variables. And you get the integral again. And this thing here is just 1. So everything that I did is exact. If you take any psi that's less than a half, you have this exact calculation here. I did it very quickly, but it's something simple. I mean, it's calculus, right? So it's nothing very complicated. I mean, the only thing that's sort of nice is that, you know, in principle, computing such an integral is very difficult. But it's nice that somehow it is the Gaussian integral after a change of variables. So you get this factor here. Right. So then you need to do something with this. So it's so you can go back here and you can say that this is 1 minus 2 theta divided by n raised to n. Oh, raised to n over 2. And then you need to do something with that, right? So the main point, essentially, is to notice, well, okay, so what does this look like here? So in our example, this is going to be just theta, right? Because we said that expectation equals 1. What about this? So you can do all sorts of things. You can take the logarithm of this and expand around theta equals 0. And you have this n over 2 here. Essentially, this is something like 1 plus theta squared over n, the whole expression. Or, okay, it's more like this, perhaps. At least if theta is less than n, which is something like that you need because of what's over here. So all I claim now is that if you take this expression and plug it over here, you're going to get something like inf e to the minus theta t. Then you get e to the minus theta, e to the plus theta, which cancels, and then you get this thing here. And then you have something very nice, which is a parabola here. It's easy to minimize this, right, to minimize this expression. And then you get this e to the minus t squared n divided by some constant. Well, I mean, I haven't been very precise with the constant here, so I said you get 16. The 16 comes from somewhere, right? This approximation is not going to be good for all theta, as I said, because this is going to blow up if you take theta going to n over 2. So you need some sort of restriction on the range of theta, and then the approximation gets worse when you make theta larger. But essentially, that's all there is to this calculation. You just do this thing. And just this general method of using Bernstein's trick to compute to bound this sort of quantity is extremely powerful. I mean, it's what you use when you prove the basic Cramer large deviations theorem. It was what you use in many, many other settings where you don't necessarily want a large deviations principle. You just want an upper bound. And, well, and there's a lot more to be said about it, but I'll just leave it here. And when we come back at 3:30, we're going to start talking about a different topic, which nevertheless is very related to all of this, and it's called compressed sensing. So stay tuned.